Hi, in this video, we want to talk about missing values, zeros, and below detection limit data when we're dealing with composition data. Okay, so with compositional data, what we've got going on is I have non-negative values and my values add up to a constant. Now, a constant value typically is a 1, so like if I have like fraction of the observations or probability vectors, or it could be 100 if I'm dealing with percentages, or maybe like 1,000,000 for parts per million. So in compositional data, we have non-negative values. So typically we're wanting to have positives, which we'll talk about in a moment. And so it would be 0 or positive for every single entry. And so the state space here is very different than our classic statistics point of view, because the geometry is just very different, since everything is restricted to having that constant sum. A major impact of this is correlations, because if one value goes up, somewhere another value must go down to maintain that constant sum of positive or 0 values. All right, now what we're going to go over is coming from Geostatistics for compositional data with R, Chapter 2. Here is the name of the authors. Students at the University of Central Florida can download the PDF of this textbook through the library. Here is the GitHub page for the package accompanying the book. Here's one of the author's professional websites. And here is the CRAN page for the package. All right, so let's get down to this. All right, so the geometry and the algebraic geometry in the algebra of the state space is very different than what we're typically used to with the Euclidean higher dimensions, which is how we model almost all statistics. But now I have that restriction that things have to add up to 1 or add up to 100 or add up to 1,000,000. I'm typically going to say add up to 1 because that's the easiest for me. All right, well, because of the difference between the geometries, we're going to end up using a lot of logarithms, and we're going to end up doing a lot of ratios. And if I have zeros, these are going to cause problems. So if I have zeros going on, I can't take a ratio with that 0 in the denominator, first and foremost. Also, logarithms can't have 0 in them. Now, in the limit, we would get negative infinity if I was to look at what happens as a value goes towards 0. The limit would be negative infinity, but that doesn't really make sense from a data point of view, right? If I take a mean of negative infinity with any other number, I'm going to get negative infinity. So it's going to be very problematic. We don't want infinity in our data set, after I do a transformation. Also, if we want to have a complete geometric framework from a previous video for algebraic geometry, we're going to be doing perturbations. So in regular old Euclidean geometry, I add vectors by adding them together. In this situation of compositional data, that won't make sense. It won't work out. Things won't work out. Things will break down from an algebra point of view. And so what we're going to do instead, to have the equivalent operation in this different state space, is that instead of adding components, I'm going to multiply components together. Individual entries for each vector, same position will be multiplied. And then after I do the multiplication, I'm going to rescale the vector to be the value that I need it to be, either 1, 100, 1,000,000, whatever it is. Okay, so now if I'm doing a perturbation and I have a 0, then what's going to end up happening is that 0 is, 0 times anything is 0. And I'm going to end up just having a 0 inserted where previously one of the entries may not have been 0. And so 0 values kind of like eat up the individual entries. And an aspect of this is that I can't like undo that operation. So in abstract algebra, we have something called the inverse of the element. And we always want to be able to undo an operation if we can in algebra. And we lose that if I have zeros in there. If I have any old value in that's not zero, I do the multiplication. I can, you go through and undo that operation, get the original if I have to, from an abstract algebra point of view. And that's very nice. So the equivalent in Euclidean geometry is that if I add two vectors, I can subtract one off, and boom, I get the original vector before it was added to the other. And I can do that undoing step here with perturbations as long as I don't allow zeros. And so we really, 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 really don't want zeros in composition data, but you know what? They can come up. All right, so when I have a zero, I need to make a choice. How am I going to handle that? All right, well, I'm not going to fully answer that question because it's a subjective decision. I'm just going to talk about different approaches, different points of view that the authors of the textbook talked about. All right, so the package that I referred to a moment ago, they have several types of missing values and zero values. And so there's four of them for how they code it. There's first and foremost missing at random, and this package codes missing at random as NaN, not a number. The amount was not observed or is otherwise missing in a way unrelated to its actual value. This is the nice type of missing. All right, so here, something that's very important is unrelated to its actual value. All right, so when we say missing at random, it's just not there. Maybe someone didn't record it. Maybe the instrument that was needed for the analysis broke down. Maybe it just wasn't possible to collect it given the situation. Maybe the sample was polluted so that we couldn't trust it, so it wasn't recorded. So like here, there's no relationship with the magnitude that we would have had of the number with it being missing. Now, next one is missing not at random, this package codes as NA. The amount was not observed or is otherwise missing, but it was missing in a way stochastically dependent on its actual value. So it was missed in a way that was stochastically dependent on its actual value. So some way, the value that is there, that would have been there, had influence on the fact that it was missing. Now, the next one is the below detection limits aspect. And what will happen here, this package, either it will be coded as a zero, or it will be a negative number where the absolute value is below detection limits. All right, so in this situation with detection limits, my tools for analysis can only go so low before it can't really interpret what's going on. So what this package does, when it has a value below detection limits in the data, it says, well, below this level, it doesn't make sense, don't trust it. It still keeps it in there, but it slaps a negative sign in front of it so that I know not to trust that value. It's too small. The amount was observed, but it turns out to be so low that I can't trust it, and it might have been rounded off to zero. And so this is like an informative version of missing not at random. Now, the next one is structural zero, which is coded by negative infinity. The amount is absolutely zero due to structural reasons. So a soil sample was dried before the analysis, or the sample was pre-processed so that the fraction is removed. So like if I was measuring the amount of water, dried the sample, then it's just structurally zero. Structural zeros are mainly treated as missing at random, even though they are a kind of missing not at random. All right, now we can extend these four types of missing and zero values to these other classes. And so we can have not a missing value. So a non-missing value is it's just a regular old data point. It's a real number. It's positive or zero. And it's just the value as is. And so here, when I say this, if it's zero, that means it's a true correct zero, even though that's what we don't want to have in the data. There's also wider missing not at random. So this is below detection limits and missing at random combined into one category. And then wider zero, This is below detection limits or structural zero. Now let's talk about some replacement strategies. A common strategy is to replace these regular values followed by the application of spatial techniques. And so here I would do, you think like interpret, or I would do imputation using the spatial aspect of my data. An alternative is an integrated approach dealing with zeros and spatial dependence simultaneously. Now, the composition zero place function replaces zeros and below detection limits observed in the composition. It will go through and take care of this automatically for us. If detection limits of each part is given, zeros from each column of the data is replaced by the corresponding detection limit contained there, scaled down by a scalar value. That scalar value by default is 2/3. The detection limit should be a vector of the length equal to the number of fields I have in my composition, or a matrix of the same shape as the composition data. And so if I have a vector corresponding to the number of columns that I have in my composition, then I'm applying that criteria to the entire the entire column. If I want to have a matrix where maybe things changed in the process of detection, maybe I got new equipment, maybe equipment broke, and now I have to change the detection limit, then I can have a matrix of the same size as my composition data, indicating what the detection limit was. If if detection limits are not provided, then the detection limit is extracted from the data set. If there are negative numbers and detection limits are not provided, it uses these negative numbers to identify what the detection limit would be. If no negative numbers are present in the data set and detection limits are not provided, the result will just be equal to whatever was entered. When a detection limit is used to replace zero, the detection limit is multiplied by a fraction for the replacement value. Okay, so here I'm saying that I have a lower bound on the values that I can trust in my data. I see something below that value, or I see maybe zero, or a value below that. Now, what this function does is it goes, well, okay, I see that this is the limit that I can trust. Let's go ahead and say I'm going to multiply that by 2/3, and I'm going to fill in the zeros. I'm going to fill in the missing values with that 2/3 of the lower limit. All right, and the default is 2/3. We could also reasonably say, well, I know the value is between 0, and I know it's between the lower limit of detection. So let's do the midpoint. The midpoint would be, I just cut the detection limit in half. Now, another point of view might say, well, you know what? These are going to give me pretty small values. I don't want extreme values in my data set, because of that whole asymptote in the logarithms. So what I'm going to do is I'm just going to use a 1, which is anytime I have a missing value or below detection limit, I'm going to replace it with the detection limit itself. All these are reasonable ways to go. Now, if I was in a situation where my algebraic geometry did not call for this, I wouldn't be doing this. I would just leave values as is. I would leave a 0 as a 0. But for me to be able to get the algebraic, geometric, mathematical properties that I want for my full power analysis, I need to make sure I don't have zeros. I need to make sure that numbers are at least a certain height, they're certain value to be sufficient. All right, so now what I'm going to do is I can use the acomp function to take care of the filling in the replacing negative values with the 2/3 detection limit value, also replacing the zeros. Okay, and we can also use so this sets up the the detection limit aspect on the composition data, And then the zero replace function is the one that actually goes in and does the replacements. A is our scalar value. And so you can see that 2/3 here. So by default, this is going to take the detection limit. If I have a 0 or a missing value or below detection limit value, it's going to take the detection limit, multiply by 2/3. That's the value that gets imputed. Now, there are arguments for using random replacement values. And so the author gives this as an approach. I don't think this actually does what the author intended it to do, because it's going to end up looking very different than what I anticipated. But the concept is solid. Now, I disagree with the idea of random replacements. Random replacement tends to look better when I do my univariate analysis, but really I don't care about the distribution of my univariate analysis. I care about the full composition of my model. In my machine learning experience, I prefer not to do the random assignment imputation techniques, but some people prefer it. It's a tool in your tool belt. Here we are using a random uniform value of the from 0 to twice the detection limit value. Now, there are several approaches for incorporating information about other non-missing components in the replacement procedure. The idea is to always to replace the missing value by some value of the conditional distribution of the missing value given the non-missing observation, be it the expected value or a random realization. So, for example, we use expectation maximization to produce a conditional expected values and then fill in the blanks using that. We could also use a Markov chain series for realizations of the missing values. This is very common in SAS, by the way. The problem with most of the proposed replacement methods is that they ignore relevant information about the dependence between the missing value and other co-located variables, or they ignore the information between missing values at a certain location and its surrounding values. So it fails to use the spatial aspects. So these failures can distort the covariance between the variables and certain and create like a more of a nuggety aspect of clumping in the observations of our data. So unstructured replacements should only be applied if the number of such values is below, the number of such values needing to be imputed is relatively small compared to my total data set. All right, so I hope you've enjoyed this video. Just a quick look at taking care of missing values and below detection limits and zeros in composition data. Life is short. Do math.